All right, guys, welcome to the Area and Volumes FRQ notes. So when it comes to the FRQs that involve area and volume, here are the things that are in common here. They're usually calculator active. However, they can be non-calculator active, so we'll talk about that a little bit. Common questions you can expect is to find area between two curves, finding volumes of solids with known cross-sections, and finding volumes of rotation. And with all these questions, it can be done with respect to y or with respect to x. So let's go ahead and start off talking about how to find area between two curves. So first of all, with respect to x, if you want to find the area between two curves that might look like this, for instance, basically what you would need to do is you would take the function on the top and subtract from it the function on the bottom, and then you would integrate from the left endpoint, which is a, to the right endpoint, which is b. So using these particular letters and numbers up here on this graph, we would have this integral, which represents this green area. Now you can also integrate with respect to y, and that's if you have these like sideways looking functions that are in terms of y. In that case, it's going to be the right function minus the left function, and the limits for your integral would be the bottom limit, which is c, up to the top limit, which is d. And so that would look something like that. Matter of fact, I just noticed there's a typo on here, and I'm going to fix that right now. The typo is that should be a dy right there. So that is how to find area between two curves. Now, sometimes curves will intersect, and when that happens, for the one half of the area, you'll have the one function on top, but for the other half, it'll be on the bottom. So as you can see here, the g is on top on the left half of the area, but on the right half of the bottom, now the g is on the bottom. Now, there's two ways to handle this particular situation. If you have to do these sorts of problems without a calculator, the first thing you're going to want to do is find where those two functions are intersecting by setting the g function equal to the f function and solving for x. The next thing you're going to do is you're going to set it up. So you're going to start at the leftmost endpoint, and you go up to the first place where they intersect. In other words, the first region of intersection there, and it's top minus bottom. And then plus, from there we start where that one left off at the intersection point, and we integrate up until we get to the end of the area that we want to find. So it goes from left to intersection, then from intersection to right, but no matter what, it's top minus bottom. Now what you'll notice is that on this one, it goes from 0 to a, so from 0 to a is the first area, and then from a to 1 is the second area, okay? Now, you'll also notice that in the first integral, it's g minus f, and that's because the g is on top and the f function's on the bottom. But for the next integral, you'll notice that it's f on top and g on the bottom, because that's how they are set up. And a little review, if you don't know which one's on top, which is pretty rare because usually with these types of questions, they give you the picture anyway. But if you don't know because they don't give you a picture, then the way that you can find out which one's on top is by just plugging a number in. Like, for instance, if you picked a number between a and 1 and plugged it into both g and f, whichever one comes out greater is the one that's on top. Now, usually, though, like I said, most of the time, these types of questions are done with a calculator, and in those cases, it's much easier. You just integrate from the leftmost endpoint up to the rightmost endpoint. So you skip the intersection point altogether. You just go from 0 to 1 with one integral, and you just do the absolute value of their difference. And that's because the absolute value of g minus f is the same thing as the absolute value of f minus g. And therefore, by integral properties, since this one leaves off where this one picks up, you could just put them together as one in that case, so long as their integrands are the same, which they would be. So with a calculator, you can just do it this way. So let's go ahead and begin our first example problem here to put these principles into practice. So let f and g be the functions given by f of x equals this and g of x equals this, and here's the picture, and they've labeled them for us. Let R be this shaded region in the first quadrant closed by the y-axis, so this is our leftmost boundary, and the graphs of f and g. And S is going to be the area that is shaded in the first quadrant and is closed by f and g only, and they don't have to tell us where it stops because it stops where they cross there. All right, and that's pretty much it. So the first thing we want to do is, let's say I wanted to find the area of the entire shaded region. Well, if this is a calculator-friendly question, which I'm going to say it is a calculator-friendly question. This is an actual FRQ that I pulled. This is a calculator-friendly question. You're allowed to use it. What we're going to do to find our answer is we're going to just do the integral from the left endpoint, which is 0, all the way up to the right endpoint, which we don't know yet, but we do know it's where they cross. So we're going to have to use our calculator to get that. Next, since we're using our calculator, we can just do absolute value and just do f minus g, and it doesn't really matter what order they're in because, like I said, when you do absolute value, it kind of ignores that part. Okay, and so then we have dx. So as you can see, what I'm going to need to do on my graphing calculator is I'm going to need to graph this function here, and I'm going to need to graph this function here, and I'm going to have to find out where it is that they're crossing. Once I do that, I can set up my integral and put that intersection point up here. So let's go ahead and do that. So I've got my functions typed in here under the y equals screen. You'll notice some things I want you guys to be remembering here, that fractions go in parentheses, and when you do your exponent here, that's a negative x, so make sure you push the negative button on the calculator, which is the one right down here, and not the minus button. All right, that being said, let's go ahead and take a look at our graph here. Now that's a really big view, and I want to zoom in only on the part that I care about. Now they don't really tell us in the problem where we care about, but we could tell it's right here. That's where the two functions are crossing. So I'm going to zoom in on that section. So I want my x values to go from 0 up to, maybe that's a 1. I think I'm going to go all the way up to maybe like 1.5 though, just to be careful. And then for my y values, I'm going to go from 0 up to 2. All right, so let's go ahead and do that. So we push window. We're going to clear out what's in x there, and I'm going to go from 0 up to, we decided 1.5 would probably be sufficient. And then for the y values, we're going to go from 0 up to about 2 is what we decided. And that way we get a little bit more of a graph that looks like what we have on the paper that we're looking at. All right, so now we know that we want to find this intersection point over here. So let's go ahead and do that. We push second, calc, we select 5 for intersection, and we scroll until we get to where the two lines are crossing. We push enter 3 times, and the intersection happens to be at x equals 1. So now I'm ready to go ahead and put in the integral that I had typed earlier. So I'm going to go ahead and push second, quit. I'm going to go to my home screen. We're going to go to Math 9 to put in an integral. And we're going to be integrating from 0 up to that intersection point, which we said was 1. Then we're going to put absolute value in there by pushing math, scrolling over to numbers, and then pushing 1 for absolute value. And we're going to do the first function minus the second function. And it really doesn't matter which one you put first because, like we said, with absolute value, that kind of negates the whole importance of which one comes first. Finally, we'll put our dx in and equals, and we'll have the area between those two curves on that interval. All right. Now, as for the next part of this question, let's move on to part B. This one wants us just to find the area of R. So if you want to just find the area of R, then we need to find this intersection point right here, because we're going to be integrating from here up to here because that's where R stops, right? And so 0 up to that intersection point. And at this point, since I'm not doing an intersection, we really can just do top minus bottom and ignore the absolute values. In this case, the g function is on top, so I would do g minus f, and that way I don't need to use absolute value bars, and my calculator can also find that answer a little bit more quickly. Now on my calculator, I called the g function y2 and the f function y1, but just be careful to know that that's how we're going to type it on our calculator, but we don't want to write that on our paper because our AP graders are not going to be aware of what we're calling y1 and y2 unless you specifically label it that way. So let's revisit our graph. This time R is this little area here, and I want to find this point where they're crossing. So same thing as last time, second, trace, 5, scroll to where they cross, and we'll find where they're intersecting. We're going to push enter 3 times. And we have our answer. Now that's a really weird number. We could write it down, but this time I'm going to store it. So the way that you store it is you push enter, and then you push store, and then alpha A. And my calculator will store that entire answer under the letter A. So now I'm going to do the integral. We're going to do math, 9. The area for R goes from 0 up to A. And we want to make sure we have the order right this time because I'm not going to use the absolute value bars. So it's going to be y2, which is the g, minus y1, which was the f function. And so the R area would have this one. Now, as for the last question here on this worksheet, for area, or part C, it says find the area of S. That one's really going to be quite the same. I'm not going to calculate this one, but for this one, you're going to start at A. You're going to end at where they cross, which we said earlier was 1. And for this one, F is on top and G is on the bottom, so we would do F minus G. Okay, now I'm not going to put it in my calculator just to save time on the video, but that's how you would at least set it up. Okay, so let's go ahead and move on to the next part of our notes here. Let's talk about volumes with known cross sections. There's 3 steps to this. The first thing you need to do is identify the base. So what is the base? Well, they're always going to give you a graph of 2 areas that are crossing. But the thing is that we want to think of that in a 3-dimensional sense. So I'm going to take this image and lay it down in a 3-dimensional plane. Now the distance between the red line and the blue line, which can be found by doing F minus G, or once again, top minus bottom, that distance represents the base of the shape that we're going to stack on top of that, which is represented here under step 2. So if you imagine stacking a square on top of that little black line, you would get this kind of a shape. So step 2 is to find the area of that cross section. So the area of a square is equal to that base length squared. And so that base length is f of x minus g of x, so the square's area will be f of x minus g of x squared. The final thing is to put an infinite number of squares on there between the 2 functions and add them all together, and that creates a volume of a solid. And the way that we add together an infinite number of things is by doing an integral. So the volume of the solid is found by doing an integral from the left endpoint to the right endpoint of the cross section's area. And for this case, it would be from A to B with f of x minus g of x squared because it's a square. Now, this formula, though, in here will be slightly different depending on what shape you're stacking on top. So some common cross-section areas would include things like the square, which we've already said is the base squared, or the rectangle. A rectangle is base times height. And usually the height is going to be given to you defined as some multiple of the base. So instead of height, we would call it something times the base, which would cause it to be the whole area to become k times the base squared. Another really common one on the AP test is the isosceles right triangle. But there are others, and we talked about them. Matter of fact, one of your practice problems for this week is going to have a semicircle on it, which we'll talk about in that when we get there. So now the cross sections that you put on there could be perpendicular to the x-axis, in which case the bases would look like this. They would be vertical lines because they're perpendicular to the x-axis. And when that's the case, you have your area of your cross section, and your limits are left and right-handed limits. It's important to understand that your bases will be the top function minus the bottom function, and your functions are in terms of x. Now, we could also do cross sections that are perpendicular to the y-axis, and in that case, your cross sections will look like this. They'll be horizontal lines because they're perpendicular to the y-axis, and when that happens, your integral is going to be with respect to y, and you're going to be integrating from the bottom point up to the top point. And in those cases, the base length will be the right function minus the left function instead of top minus bottom. Also, your functions will be in terms of, let me move this out of the way, your functions are in terms of y instead of terms of x. All right, so let R be the region in the first and second quadrants bounded by this graph below by the horizontal line y equals 2. So basically, I'm going to visualize this. We don't know. You don't need to draw this right now, but I've got this function. I don't know what it looks like, but that's the one that's above. And then I have this horizontal line, which is the one below. And it says that the region R is the base of the solid. The cross sections perpendicular to x-axis are semicircles. So it says it's in the first and second quadrants. So that's why I only graphed it in these two quadrants up here. So we have the y function on top and the y equals 2 here, and it's only in the first two quadrants. Now, this once again is a calculator-based question, so we can actually see the graph for ourselves, but we just need to make sure that we stick only to those top two quadrants. So let's go ahead and do that. So I'm going to let y1 be the 20 over 1 plus x squared. And remember, anytime your denominator or numerator has more than one term, you need to use parentheses. I'm going to let y2 be the function on the bottom, which is the function 2. So we'll look at a graph of this. And we only care about the first quadrant and the second quadrant. Now, I can't see the top of the blue line. So let's go ahead and go a little bit higher with our view here. Also, we only really need to go out to maybe x equals, let's go out to x equals 4 and negative 4. So my window, my x values really only need to go from negative 4 to positive 4. And as for the height, I don't know. We know the y, the minimum is 0. It doesn't need to go below the y-axis, but the max 10's not high enough. Let's go ahead and try 20 and see what that looks like. That's a little bit better. So basically, I want to find this area here between these two functions, kind of. That's actually the base of my shape. So now that we've got our picture here, let's revisit the question that we're looking at. So that's the area we're looking at. They didn't give us a picture this time, but we made it. Now here's where the real question lies. It says, the region R is the base of a solid. The cross sections are perpendicular to the x-axis. Now that's important. So I'm going to draw this shape again here really quick. It looks something like this. My cross sections are perpendicular to the x-axis, which means that we're going this way, which means that my integral is going to be with respect to x, and it's going to be the left endpoint minus the right endpoint. Now the left and right endpoint are the places where they're crossing, so I need to find out where they're crossing. Second of all, it tells me that the cross sections are semicircles. Now you guys might not remember this, so something to put, look back in your notes on if you need to, but this was not real common on the AP exam, but I'll give it to you anyway. The area of a cross section of a semicircle can be found in a few ways, but the way we did it in this particular lesson was pi over 8 times the base squared. And the base is, as you know, the top function minus the bottom function. So that would be this function, which I'll call y1, and this function, which I'll call y2. So this area is going to be pi over 8 times y1 minus y2 squared. Okay? Now on my paper, though, I think what I'll write is this. First of all, those constants, I'm going to encourage you guys to always make sure you put those out in the front. Second of all, unless you want to name these functions y1 and y2 on your paper, it might be good just to go ahead and actually write them out. But if you wanted to actually name them y1 and y2, then you can go ahead and write that on your paper. Now, if you want to be safe because you're not sure about which one should go first, remember, just put absolute value bars on it and you're safe. Actually, since it's being squared, I take that back. We don't need absolute value bars at all because when you square something, that also gets rid of negatives. So all I need to do to complete this integral is I need to figure out what the left and the right-handed endpoints are. And on my paper, you want to make sure you don't put L and R there. You actually need to find those and put them on your paper. So let's go ahead and do that really quick. Let's revisit our calculator and see if we can find those points of intersection. Same thing we've done before. Second, calc, 5. We're going to scroll on over to where they're crossing. We're going to push enter 3 times. And it's negative 3. That's pretty nice. So I'm not going to store that because I can remember that number and I don't need to round it. Now something tells me the other side is going to be positive 3, but I'm going to check just to be sure. So we're going to do second, calc, 5 for intersect, and we're going to scroll to where they're crossing. And I'm pretty sure that's going to end up being 3 also. Yep, sure enough, it's 3. All right, cool. So back to this then. So now we can go ahead and complete our integral. We're going to put a -3 on the bottom here and a +3 on the top. This is what you would want to write on your paper, and typically on the FRQs, this will be worth 1 point, just writing that correctly. The second point will be actually calculating the answer on the calculator. So let's go ahead and do that also. So we're going to go back to our home screen. We're going to push Math 9. We're going from -3 on up to +3. We're going to be doing the quantity of y1 minus y2. Notice I'm putting that y1 minus y2 in parentheses. I'm not using absolute value bars, although you could. And then I'm going to square it. I'm going to go ahead and scroll over. We're going to put our x there. And at that point, we should be able to get that volume of the solid that's created in that. Oh, and you know what? I forgot my pi over 8. So I should have had a pi over 8 there in the front, and I forgot to put it there. So my bad. I should have done that in the beginning. If I had done that, you want to put that in parentheses. But now that I've forgotten, I think what I'm going to go ahead and do is I'm just going to go ahead and take my answer, and I'm going to multiply the answer by that value of pi over 8, because it's literally the same thing if we just do it in 2 steps instead of 1. But there we go. So actually, that's the final answer, is 174.268. Don't forget, on AP Calculus exams, you round to the thousandth place. All right, so that's volumes of cross sections. Let's talk about volumes of rotation. There's 2 types of volumes of rotation. There's the disk method and the washer method. So we'll start off with the disk method. So first of all, let's talk about when you're rotating around a horizontal axis of rotation. So first of all, you need to find your radius of the circle that is created by this rotation. And that's found by just doing your function minus the axis. So for instance, on this particular shape, let's say I wanted to rotate this function here around this horizontal axis here. The distance between those is my radius, so I'll label that r. Now, technically, it should be top minus bottom, whichever one's on top, but it doesn't really matter because when we do these problems, you end up squaring this, so that kind of eliminates the importance of the order of these things. Now, once again, want to think of this in a 3-dimensional sense. So if we lay it down, it looks like this, and now my radius is here. Now, if I go ahead and rotate this, it creates a circle. And if we do that an infinite number of times, we end up creating a 3-dimensional shape, which would look like this shape here. And the integral is pi r squared. That's the area of one of the circles. And since we're integrating from the left endpoint to the right endpoint, that's like adding all those circles together to create a volume. Okay, so the way that you do a volume of rotation with the disk method is you find your radius, which is function minus axis. You square that radius, and you integrate from left to right with a pi multiple in the front. You have to remember, though, that if you're going around a horizontal axis of rotation, you're doing this with respect to x. Your limits are left to right. Your functions are in terms of x. Okay? Now, if you ever have a vertical axis of rotation, you're still going to have a radius, which is function minus axis, but this time, if you're going around a vertical axis, your radius is going to be like this, perpendicular to the y-axis, or it's perpendicular to the axis of rotation, which is vertical like that. And once again, thinking about that 3-dimensionally, it would look like this, and so your radius is here. Now, the way that you're going to do this is pretty much the same. You're still going to create a volume. It's just going to be rotated vertically instead of horizontally. It's still pi r squared, but the difference is that your integration is from the bottom endpoint up to the top endpoint. Instead of left to right, it's bottom to top. And also, it's with respect to y, and therefore your functions need to be in terms of y. All right. Now, the next thing I'd like to talk about is volumes of rotation with the washer method. Now, the only difference between these is that with the disk method, you have one function going around an axis. But with the washer method, you have 2 functions being rotated simultaneously around an axis. Okay. Now, when that happens, when you rotate it, you don't get a solid, you get a solid with a hole in the middle of it, okay? And that's because there's a gap between the two functions areas that you're rotating and the axis that you're actually rotating them around. So let's go ahead and talk about how to do this. So since you're rotating two functions, you're going to have two radiuses. You're going to have a big radius, which is the function that's farthest away from the axis down to the axis, and that's your big radius. So the function that's farthest minus the axis will give you the big radius. Then you're going to find the distance of the function that's closer to the axis, and you find that distance by doing function closest to the axis minus the axis. So that's your big radius and your little radius. And then what you're going to do is you're going to find the area of your big circle, which is pi r squared, and you're going to subtract from it the area of your little circle, which is pi r squared. So the pi we're going to just put out in front. That's important. A lot of you guys in this lesson were putting it inside. Don't do that. It leads to errors. Just make sure that pi is on the outside. And we do big radius squared minus little radius squared, and the order does matter. If you do it backwards, you're going to get the same answer, but it will be negative, and you should not be getting a negative answer. So if you do get it negative, two-step process is an easy fix. First of all, just change the sign of your answer and write it positive. Second of all, go back and erase these and reverse them. You don't have to recalculate anything. It's going to literally come out the same. It's just that you wrote it backwards, so you have to fix it. And once again, you just go from the left endpoint to the right. Now, I only included in an example here that's being done with respect to x, but you can do these things with respect to y. It's just that the same principles that apply to the disk method apply here in that respect. So let's go ahead and take a look at one more example, and that'll be the end of our notes for the day. So we have this region R here, and it's bounded by the graphs of ln and x minus 2. Now, we're going to graph these to figure out which is which, but I think you guys could probably tell from some basic math knowledge that x minus 2 is going to be this straight line right here. That's the x minus 2, whereas the curving line is going to be the ln function there. All right. Now, I want to find the volume of the solid that is generated by rotating it around the line y equals -3. Now, I don't know where y equals -3 is, but because I don't know how far down this point is, but I'm going to assume it's below the area. So let's just say this is the line y equals -3. Okay. So to do this, since I'm going around a horizontal axis, my integral is going to be with respect to x, which means we're going to go from the leftmost endpoint, which I'll call x1, to the rightmost endpoint, which I'll call x2. So on our graphing calculator, we're going to have to find out what those things are. Next, the radius is going, well, in this case, notice that we have two functions, right? And when we have two functions being rotated around an axis, that's the washer method. So we're going to have a big radius squared minus a little radius squared. And the pi is going to go in the front. All right? So my big radius is going to be the distance of my ln function from -3. And that can be found by doing that function, ln of x minus a -3, which is just ln of x plus 3. That's my big radius. Now my little radius is going to be the distance of this blue line to the axis of rotation. And that's going to be the function x minus 2 minus 3, which simplifies into x minus 5. How did I know this was my big and how did I know this was my small? Because once again, the big one is the one that's farther away from the axis. The little one's the one that's closer to the axis of rotation. And so basically, I'm going to put my big radius here. I'm going to put my little radius here, and then we're going to calculate it. Now, let's go ahead and go to our calculator. We've got a few things that we need to do. We need to put these functions here into our calculator. We also need to put the intersection points, find out what those intersection points are. So let's go ahead and jump on over to the calculator here. All right, so I've got my functions plugged in there. We're going to go ahead and graph it. We're probably going to have to adjust our window a little bit. I want to zoom in on this area, so I want my y values to go from like -4 up to about 2 on the y-axis. And then for the x-axis, we're just going to go from 0 to about maybe 4. So let's go ahead and adjust that a little bit. And that way we'll get a little bit of a prettier graph to look at here. I also want to, well, actually, I think that's probably good enough. Let's go ahead and find where those lines are crossing now. So we want to do second, calc, 5, and we're going to scroll to where they're crossing. So here we go. 1, 2, 3. So we have 3.1461932. I'm going to save that. So I'm going to push enter. I'm going to push store. Oh, sometimes this doesn't work for me. Let me try. All right, and so there's my first intersection point. We're going to go back. I've stored it under A. Now we're going to go ahead and push second calc. We're going to find that other intersection point. Once again, you push second calc and then 5 for intersect. Scroll to where they're meeting approximately and push enter 3 times. And there's my other intersection point. Once again, I'm going to store that. And we get that. All right. And so now I'm ready to go ahead and type in my function here. As we said before, it's going to look like this. It's going to be the integral with a pi in the front. And my leftmost endpoint was B. My uppermost endpoint was A. And then it's going to be the big radius, which is the ln function, which I typed in under y1. So I'm going to call that y1 minus the axis 3 here, minus the big function, which I called the other function, which is the little radius, which was y2 minus, actually it's going to be plus 3, because we're subtracting a negative. I take that back. And then we square it. And we're doing this with respect to x because we're rotating around a horizontal axis. All right, so we're going to go ahead and type that into our calculator now. So without any further ado, here we go, math. Actually, you know what? Let me go back. Before I do math this time, I'm not going to forget my pi this time. I'm going to put pi first, and then I'm going to do math 9. I'm going to put my alpha b on the bottom. I'm going to put my alpha a on the top. And then we're going to do one set of parentheses with y1 first, minus a negative 3, but I'm just going to put plus 3 because when you subtract a negative, it's like plusing. And that's the axis. We square it, minus the little radius, so that's going to be the same thing. We just type it with a y2 instead. And of course, we need to put our dx there at the end and enter, and that'll give us the volume of that shape. All right, as for the last part of this FRQ example here, we're going to do another one. We're going to do another volume of rotation. This time we're going to go around the y-axis. Now in that case, the y-axis is a vertical axis of rotation. So in that case, what we're going to have to do is we're going to have to remember we're integrating with respect to y. Furthermore, I also need to remember that my functions need to be in terms of y. So that's going to make for things to be a little bit trickier, okay? So first of all, I have y equals ln of x. Well, that function is a function that's in terms of x. So I need to change that into a function that's in terms of y. And the way we do that is by solving for x. How do I get rid of an ln? Well, you e both sides. I'll just call it eing both sides, although I think that's probably not the right way. I think you're supposed to say exponentiate, but that's fine. But if we just make both sides a power of e, these will cancel, and now I've got this. And so now this function on the top here, that's going to be called x equals e to the y. Now the function on the bottom here, the red one, we also need to get that one to be a function in terms of y. So right now we have y equals x minus 2. But if I want to get this function to have x by itself, I would just add 2 on both sides, and I would have y plus 2 equals x. So now I'm going to call this function down here y plus 2 equals x. Okay, so there's my first hurdle I need to get over there. Now the next thing is we need to figure out what my big radius is and what my little radius is. So my big radius is what's going to go here first. Now the big radius is the function that's farthest away from the axis. So you guys tell me, which line in general is closer to the vertical axis? Like if you picked this point right here, all the way across that particular value of y, which one's closer? As you guys can see, the blue one's closer to the axis than the red one. So this one's going to be y plus 2 That's the function that's farthest away from the axis minus the axis. Now the y-axis is the equation 0, so we're just going to put 0 there. The little radius is going to be the one that's closer. That's the blue line. Now the blue line then will be e to the y minus 0. Now, as you guys may know, we could simplify this. We really don't need the plus 0 in there. And so what we could do is we could really just put y plus 2, and we could really just put e to the y, because 0 doesn't really do anything, right? So we could really just write it like that. But I just wanted to write it out so you guys can kind of see the process is really the same. Now there's one other important difference when you're trying to do things rotated around vertical axes. Your limits are not going to be x values anymore, they're going to be the y values. So I have to go back and I have to find these points of intersection again, and this time I have to have the y values for the point of intersection. Okay, so let's go ahead and do that. So second, calc 5, and enter 3 times. So there it is. Now, our calculator, unfortunately, as far as I know, has no way to store y values. It only does it for the x values. So I'm going to need to actually write that off somewhere so I don't forget about it. And I think I'm going to go a little bit beyond the mere 3 points that they ask, or the three numbers after the decimal that they ask for, just because I want to make sure my answer is as accurate as possible. So that's going to be the leftmost endpoint. I'll call that one A. Next, we'll go ahead and do B, which is the, actually, I probably shouldn't have said leftmost endpoint. I should have said bottommost endpoint. So we're going bottom to top, right? So let's do this again. Second, calc 5. And this time we're going to scroll up and find the y value of the other intersection point. Enter 3 times. And that y value is 1.146193.2. And I'm going to write, like I said, more than just 3. Since I can't store it, I want to make sure I put as many numbers on there as possible so that my final answer, which is rounded to the thousandth place, will be as accurate as possible. All right, so let's go ahead and revisit our original expression here and put those numbers in. So this would be the final way that you should have that answer written on your paper. Now my guess is that this could be anywhere from a 3 to 4 point question. 1 point could be given for the fact that you found the intersection points. The other point could be given for the fact that you took the time to find these functions that are in terms of y. Another point could be just for the general setup of getting the integral set up, and then the final point could be for getting the answer. Now, that's probably being a little too generous, but my guess is this one would probably be worth 3, possibly worth 4 points. But now we're going to go ahead and put this into our calculator. And there you go. That's what it should look like. Now you'll notice that I'm using x's instead of y's, and that's because my calculator doesn't really give me the option of putting y's there. So we're just going to use x's anyway. Notice that I put in the full extent of those decimals just so I can have as accurate of an answer as possible. Another thing that you might notice is that instead of doing like a vars and selecting y1, I just went and typed the functions in exactly the way that they appear. You could have stored this under like y3 and stored this under y4 and just put y3 and minus the axis here, y4 minus the axis here, but I went ahead and just decided to type it in. There's a few different ways you could put it into calculator, but in any event, go ahead and type it all in, and that would be your final answer. So that's the end of our notes, and we'll see you guys in class.